a research scientist in the Heliophysics Science Division at NASA's Goddard Space Flight Center and ASTRA. He is working in support of the Solar Dynamics Observatory satellite and is the acting director of the Center for Helioanalytics. Michael received his PhD in astronomy from New Mexico State, where his research focused on automated tracking of chromospheric bright points and their connection to solar eruptions. During this time, he also worked for the Air Force Research Laboratory at the NSO in Sunspot, New Mexico. And upon graduating in 2013, he joined the Heliophysics Division at Goddard as a fellow of the NASA postdoctoral program. After receiving his bachelor's degree from Whitman College and prior to entering graduate school, Michael first worked at Goddard Space Flight Center in 2007 as a systems engineer researching the changing position and size of the polar coronal holes throughout the solar cycle. He grew up in the Willamette Valley of Oregon, and outside of work, he enjoys discovering new music and experimenting with home roasting coffee, which I am actually disappointed to only just find out about now and not know when I lived close to him. But the good news is that he's actually moving to Colorado sometime soon, so it's not all lost. And today he is going to tell us about the intersection of machine learning and heliophysics. So take it away whenever you're ready, Mike.
All right, thanks, Paul. We can talk more about home roasting coffee, but today I am excited to share with you sort of an overview of a few different projects that I've had the privilege of working on, as well as let me get set up here, as well as some ideas of where we're going into the future. And this is really looking at the intersection of machine learning as a discipline in heliophysics, and what does that look like, and why does that exist, and why is it becoming such a hot topic right now? So this all started, this process for me all started back in about 2015 when Neil Hurlburt at Lockheed posed this question to me when I was out visiting one time, which was, what science would you do with the complete SDO archive? And I had an answer for him, and I don't really remember what I said, but I can guarantee I didn't say anything very intelligent or worth remembering. But what really stuck with me was not what could you do or what would you do, but really, yeah, what could you do with this archive? And why does that actually stick with me? Well, to give you an idea, that the scale of the archive is the real issue. I mean, it's the benefit, but it's really a challenge. So what you see here is just a little visual representation of the projected total data volume over the mission lifetime, or at least projected out to 2035. And each of the boxes is scaled to represent approximately the data volume of the missions. And this is, of course, the compressed archive data volume. And you can see that all of the solar missions, both ground and space-based, GOM+, SUVI, Stereo, Hinode, RESI, they all fit into this one little corner up here. SDO is the current elephant in the room at estimated 32 petabytes of data by 2035. Again, this is compressed. And DKIST, of course, is coming online and is going to be even bigger yet. Currently, there are over 8.7 petabytes of compressed AIA images in the archive. And if you uncompress them, if you unpack them out of their Rice compression, they'd be over 20 petabytes in size. So what does that actually mean? If you were to use an optimized state-of-the-art solid-state drive operating at its theoretical maximum of 7,000 megabytes per second, it would take over 14 days to read through the entire AIA catalog. Okay, well, that's not actually very close to reality. We don't really get to those theoretical maximums unless everything is optimized. So in reality, it'd take about 500 megabytes per second read-write capabilities, or about 200 days just to read through the AIA archive. Of course, SDO has other data products involved. And if you actually wanted to do something with these images, just reading and writing them, or just reading them, opening and reading the images is not enough. You want to actually look at the images themselves. So this presents sort of a conundrum of like, we have this great data archive that is of high quality science data, and more data is coming online from SDO and soon to be DKIST in spades. But what do we actually do with it? How can we actually do science with it? How can we actually ask questions of the entire archive and not just cut out a small little portion and ask a very limited question of it? So this really leads to the rise of data science as a discipline into heliophysics. So data science is more than just machine learning and AI, but we'll talk a little bit more about that. But the idea of how do you actually use data? How do you use it efficiently? How do you query archives? How do you construct archives to actually be able to utilize the data efficiently? How do you create science questions of the archives? This is really where the idea of bringing data science into heliophysics comes from, is being able to use this data efficiently. However, I bet you most people would think of, when they think of data science, they hear about artificial intelligence and machine learning, AI and ML. You hear about it all the time. It keeps on coming up over and over again. It's the new buzzwords, and oftentimes these will be stand-in terms for data science or for something else. So let's just do a little bit of bringing ourselves onto the same page in terms of nomenclature. And so that's what I'm showing you here in this plot on the left. And so in the biggest circle, you have artificial intelligence, and artificial intelligence is a really broad category. It encompasses lots of different tools and techniques of algorithms, but in general, what artificial intelligence is algorithms that can change themselves to adapt to new data environments. And so these are changeable algorithms that somehow change the weightings or change the internal structure of the algorithms to change to new data inputs. A subsection of that, but overall the largest subsection of that is machine learning. So machine learning is a subsection of algorithms that do this kind of learning from experience, being exposed to new data and changing themselves of that. Of course, inside of this, there's the term deep learning, which you may have run across. Deep learning is really just a subset of machine learning. Deep learning just refers to that the number of hidden layers, the number of weights and parameters that go on behind the scenes that we don't actually have control over, are many layers deep. That it's not just one hidden section, one linear section from A to B, but there's actually many different subsections, many different subsamplings that will take you many layers deep. Of course, big data, the terms big data and data science are also thrown around. So how do those fit in? Well, big data really is this overlap, some of deep learning, some of all of machine learning, and some of data science. But big data refers to how you actually interact with data sets the size that we're dealing with, the petabyte-sized data scales. How do you actually go in and ask a question of them, query a petabyte worth of information, and pull out usable information out of it? And then data science sort of sits above, kind of straddling all of these different fields, where it's not just about algorithms and machine learning and deep learning and big data, but data science also starts pulling in statistics. It also starts pulling in into information representation, about how you present the information to other people, how do you communicate ideas. And so data science sort of sits above all of it, but doesn't necessarily exclusively mean machine learning and data science. So ultimately, what this all means is we are looking for functions. That's all this is. We're looking for y as a function of x. And so this could be a classification function where you're looking for this line that divides two simple populations. It could be a regression function where you're trying to fit a trend to a series of data. But ultimately, at the end of the day, what machine learning and AI do, specifically machine learning, what it does is it's just looking for functions. Of course, these are trivial examples. These are examples that are easy to do and easy to represent. But what happens when you add many more data points or many more dimensions, or a much more sophisticated and nuanced data where there are many different classes of information? And that's where really the interest comes in from an academic side of things. So the question would naturally arise, well, why a focus on data science now? I mean, I've been doing linear regression since undergrad. I mean, most people can say that you've been using these tools since undergraduate, or maybe you did neural networks back in the 70s and 80s when they were emerging science, and this is just rehashing that, isn't it? And in a sense, yeah, it is. It's just rehashing it. But the reason why there's been a revolution in the last 20 years are because of a confluence of three different pieces that have come together now. One is the data. We talked a little bit about that in terms of heliophysics data. We have new, larger databases that require these new tools to be developed. They are bigger than we've ever seen before, and they're growing exponentially. And so the amount of data that we need to use has exploded. The next one is algorithms. The algorithms have really come into their own recently. You may have heard of something of neural networks. Neural networks were developed decades ago, but recently there have been new advances that have come in that have created neural networks that actually do meaningful work and actually find meaningful trends. And so the algorithms have really been developed a lot recently. We'll talk a little bit about that. But the last thing, and one of the more critical parts, is the computational power, and specifically the GPUs, the graphics processing units. GPUs were mostly seen as tools for gaming. They were something that you would have in your desktop computer that you would only use to project graphics on your screen. If you were to actually hack into the graphics GPU and try to manipulate matrices with the GPUs, which they're very good at, you would have to essentially write in BASIC or assembly up until fairly recently. And NVIDIA is a big game changer in that they started developing data science tools that could run on GPUs specifically. So all of a sudden you could do a deconvolution routine on your GPU or on your CPU using the same bit of code. And that's really the revolution that's come in the last 10 years or so, is this accessibility to new types of computational environments and the algorithms to back that up. So specifically, computational resources have grown substantially. And the other part of computational resources is the cloud computing resources. I'm sure a lot of you have heard about cloud compute, Amazon Web Services, Google Colab. These are examples of vast computing resources that are available on demand at your desktops through the internet. But they're not enough by themselves. And so what ends up happening is that you are able to use code on your own desktop computer using a workstation like the one up here that Raphael Atier is using to develop code on your desktop, run it personally, and then transfer that up into a cloud computing environment or some sort of cluster computing if you have a high performance computing cluster on premises, and use that same computing environment both on your desktop and in these HPC environments. And that's really a revolutionary development that's happened, again, in the last 10 years or so. And additionally, the I/O procedures, input and output of data, has also been amazingly improved recently with solid-state drives. NVMe drives are now affordable to some definition of affordable, and you can get up to hundreds of terabytes now with a RAID SSD configuration. You can get on-premises petabyte-sized storage for something at about 100K. Of course, those are spinning disks; they're not state-of-the-art, but still, for a reasonable investment of about 100K, a university could do that, or an institution could do that. You can get petabyte-sized storage locally. So many of these high-performance computing environments that we used to exist in, I'm thinking like the Discover cluster at NASA Goddard, for example, weren't designed to work in these data science environments. And so a lot of these old data science or old environments for high performance computing that were really designed to run models of the universe, models of global circulation, all sorts of different models are now not really capturing the efforts of what modern data science needs in terms of read-write procedures, in terms of digesting a vast amount of data and producing more data that it consumes. So that's where these cloud computing resources from Amazon and Google have really become popular, because they are designed to handle that. They are designed to handle these modern environments. Okay, so that's kind of brings us to where this helioanalytics terms comes from. And this is really why the Center for Helioanalytics at Goddard was conceived of and put together a couple of years ago, and we're starting to form a community around this, was to bring data science, into heliophysics. So to address what are the algorithms that exist and how do you use them? How do you access the data in terms of if you wanted to pull in a large data set or access a substantial amount of information, how do you actually do that? What are the databases that you need to? It's no longer sufficient just to download it to an external drive or to your desktop, but actually how do you deal with it? And then how do you interface with the computational resources that are either on premises or in the cloud? And ultimately, how do you actually do physics with it all? So this is where this Center for Helioanalytics was formed. It was out of this idea. And this convergence at the center here is where we're living in terms of creating these examples for the community to use. And so it doesn't just remain isolated at Goddard, but it's about how do you actually leverage these resources where you are, so that we don't actually have to keep isolated at our individual institutions. So this kind of represents the outline for the rest of the talk. This is how I'll go through examples of where we're succeeding and where we're failing in some of these areas. And I'll end up with a bit of a summary and a look to the future and address a few of those ideas. To begin with, though, the consistency of data is key if you actually want to use machine learning. So here's an example of some running difference images from the LASCO C3 instrument. And you can see that these are not exactly AI-ready or analysis-ready images. And however, a lot of the images archives and a lot of the data archives in heliophysics exist in some sort of state like this, where that if you apply just a simple processing algorithm like a running difference, you end up with a lot of noise or a lot of artifacts coming into your images. And I'm sure that many of you, this is part of your regular workflow. If you're doing data analysis, you pull down your data, you run an initial prepping or calibration routine, but then you have to manually go through and assess how analysis ready the data is before you can start asking your science questions of the data, before you can do any sort of analysis. So an early example of improving on this came when Will Barnes did some initial work on Pleiades out at Ames to take the DASC routine, which is a routine that divides up jobs in a high-performance computing environment, and translate that into using AIA prep. And so he was able to divide up an individual prep routine. And for AIA, if you're not familiar, when you download an AIA image, you download a level 1 image. And that is science ready, but it's not necessarily self-consistent. So in order to make it self-consistent, you have to run through a few different steps. A minor translation might be needed. You might have to resize it to adjust for the orbit of SDO itself. You might have to do a rotation, a small rotation. And then if you want to remove a point spread function, you have to do a deconvolution as well. And that's all to prep this to a level 2 image, which is much more smooth and consistent. The image is the same size in the CCD. The calibration tables are taken into account. And so by running through these steps, you take a data set that is slightly less consistent with itself and make it extremely smooth and consistent. However, this takes time, this takes effort, and so running it just on my my personal desktop here, I think I clocked it in at about 2.5 to 3 seconds to run through the AIA prep, and then depending on how I'm running the PSF function on it, we're also talking about another few seconds to a minute, whether I'm running it on a GPU or CPU, to actually deconvolve the point spread function. Using Dask, Will was able to take this and do a demonstration of how in real time you could process some of these images to a level 2 standard. And then at Goddard, we are working on a hybrid CPU-GPU implementation of this. So it's not just using a CPU environment or a GPU environment, but actually splitting the job into multiple different environments. And we're actually able to achieve less than a second per image processing. So that means that we could actually process an image to a level 2 standard faster than SDO is actually taking the images themselves, which might actually meet an ideal of being able to serve a level 2 data product from SDO directly. So instead of having to run this sort of pre-processing routine on your personal desktop, then all of a sudden you can just ask for a level 2 product and it will be processed for you in real time and then served out to you. Something like that, or create an archive of level 2 data entirely, where you, if you want that sort of stability, that kind of data is available to you. However, with this new data environment, there are new algorithms that we can use as well. So these new innovative algorithms really open new doors and open new possibilities for the questions we can ask and how we can actually interrogate our science data itself. And really, machine learning sort of algorithms sort of branch off into 2 parts at this point. So there are supervised and unsupervised routines. So in order to explain this, I thought I would just take a step back and break it down in a diagram a little bit. So this is what sort of a cartoon workflow of a supervised machine learning tool looks like. So you have some input data that is jumbled and amorphous and has many different classes in it, many different types of shapes in this case. The algorithm itself needs input from an expert observer. So this could be a scientist, this could be an intern that is labeling things. But in order to use supervised machine learning tools, you have to have some sort of expert say, this is true and this is false. This is actually what we're trying to do. So we have a training set that is designed to train the algorithm. You have a desired output of, let's say, you want to find all of the, let's say, all the filaments in solar images. Then that desired output is encoded into the image or into the algorithm by the supervisor, by the programmer. So then there's processing, and then the output spits out the learned algorithm, that learned function that identifies these different pieces. So for example, if you're looking for filaments, it will say, here's a filament, and here are quiet sun, and here's something else entirely, for example, in these 3 classes. This is different than unsupervised machine learning, which uses the data to find trends within itself. So again, we have the same input data in this cartoon workflow example. Now, the algorithm or the interpretation itself does not necessarily have labels. We just have data that has some trends in it that we want to find. And depending on which algorithm you choose and how you set up the initial parameters of those algorithms, you can actually get one of these unsupervised machine learning tools to be able to discover trends all on its own within the data. So again, there's the algorithm processing and output where it finds these 3 cases. All right. So in order to give you an example, though, let's turn back to heliophysics images and heliophysics data, because by itself, these are fairly abstract and you might not see how they can actually apply and help with your own specific science questions and data problems. So the first example I want to give you is a supervised machine learning question. So this is using the labels of the HEC, the HelioEvents knowledge database, that is run by SPOCA, the SPOCA algorithm. So it's an algorithm that's developed by in Belgium at the Royal Observatory of Belgium. And what we wanted to do in this test, this is a project that I led a few years ago, is we wanted to be able to take these labels and actually see if we can train an algorithm to reproduce the labels, but also not have to go through learning about all the other features of the sun. We wanted to encode physical knowledge of the sun. And so that's what we're showing up here, is that we included a few different trends. For example, this little animation that you see here is the probability density distribution of sunspots over the solar cycle of where they occur. And you can see the probability bands up there. So we're able to include that as a layer into the product. We're able to include periodic functions, so that if we know that there's a 24-hour variation in the orbit or there is a yearly variation in the orbit, we're able to include those as pieces of the functions of known parts of this label to either use or discard. But it's something that is a known physical parameter or tangible parameter of the data itself. Then what we did was we encoded every single EUV layer in AIA and stacked that up and used all 7 EUV wavelengths, and I think we used 1600 and 1700 as well, plus magnetograms, plus continuum images. And we fed all of this as one giant stack of data, this giant data cube, into the algorithm to learn the labels of coronal holes, of active regions, and of sunspots. And of course, that sounds like overkill, right? Well, our reasoning behind that is that we wanted to make sure that the algorithm was ignoring the things that it needed to ignore and seeing the things it needed to see. So in other words, if you were looking for sunspots, you would never look in the EUV to find sunspots. You're not going to do a very good job finding sunspots if you're only looking at EUV images. However, looking at continuum images or possibly somewhat magnetograms, you are going to find sunspots a lot better. So by including the amount of information into the algorithm, we are actually able to trace back to make sure that in this case, it's a UNet plus LSTM, was able to track on exactly the correct physical features. The animation that you see here are the results from tracking active regions. The blue outlines are the HEC labels. The red outlines are the ones that the algorithm found. It's a pretty good agreement. It's not perfect, but it's pretty good. Now we're actually increasing the resolution. We actually had to downsample to 512 by 512 images just because of memory. But with more computational power, we're actually able to look at the images that are higher resolution and go in and do a better job of finding active regions in this case. But again, the 3 initial features that we were looking on the sun. So the supervised machine learning tools have really great potential for accelerating models of known parameters or known processes that we've already well defined. So if we have a bunch of labels from SPOCA, we can train a machine learning model to reproduce those exactly. And so instead of SPOCA taking hours to run, minutes to hours to run, this could be run in mere seconds once it's trained. All right, moving on to unsupervised machine learning. This is a way of looking at data that when you don't have labels necessarily, when you don't know what this looks like. So if you were able to take an image and decompose it and have it look for trends, this is sort of what unsupervised machine learning to do, is finding trends in the data without knowing already of what you're looking for. So this is an example from work that Benoit Tremblay led at the Helio Hack Week at Goddard back last year. So it's work that I've had the privilege of working with and continuing to advise in. And this was using a technique called a WNet. And the network architecture is up here for people who are interested in that kind of thing. But it's using a WNet, using convolutional neural network to decompose an image into its own specific groups of pixels that are self-similar to each other. How are they self-similar? Well, I mean, that becomes a little bit harder of a question to answer specifically, but you can say that edges are important, that intensity is important. And the output of all of the different classes that this WNet routine found is down here at the bottom. And this is a very colorful image, but you can start to see some physical trends starting to pop out, where a coronal hole, a polar coronal hole, it can be seen in many classes here on the bottom. Excuse me, southern polar coronal hole, and then a northern polar coronal hole up here. You can infer that some of these colors were associated with quiet suns, some with active regions. But being able to actually associate these classes back to their physical structure, that's why you need a scientist in the loop, is to actually go back and look at the data and be able to say physically, what are these different classes representing? Because by itself, the algorithm is just going through and labeling things that are self-similar. So these have great potential. These algorithms, these unsupervised algorithms, have great potential for finding new trends in data, for finding new things that are similar to each other. And so you could do some great discovery science with unsupervised machine learning. This is, of course, more challenging because you have to have physical intuition to be able to actually to prove whether it's doing something appropriate or not, because the algorithm doesn't have any physics encoded in it. It is purely using the data as the data itself. And so that's why having a strong sense of the physics and really pulling the physicists into the loop are essential when using unsupervised machine learning tools. In addition, for unsupervised learning, having an ability to translate a question from a science question into a data question can really aid in the ability of data discovery. So for an example of what I'm talking about with this is a project that I led with Barbara Thompson, looking at cosmic ray hits from AIA images. So when you have an AIA image, what happens is that as part of the level 0.5 to 1 processing, it goes through and an algorithm removes what it deems as cosmic ray spikes. So these are bright points that are relatively isolated in space, and they goes through and takes it down to the mean value of its pixels nearby. Interestingly, though, if you can identify a small, bright, compact feature that I would argue is a physically real feature, like in these series of images here, often the AIA despiking algorithm will go through and remove the peak intensity, therefore eliminating a tiny little feature on the sun. Okay, well, that's interesting, and I mean, a word of caution if you're using AIA. If you're looking at something of just a few pixels wide, definitely respike your data if you're looking at bright things, because you might change a result. But in a data science question, you can reframe this to say, oh, because we have all of these spikes that are removed and stored in a database for the occasional respiking needs, we now have a large treasure trove of data that are pixels that were bright and removed. What's in there? What are the physical definitions of those features, those single pixels that are removed? How can we translate this this image question of a small bright feature into, was this a loop eruption? Was it a jet eruption? Was it maybe a new campfire that was discovered by Solar Orbiter that AIA so happened to see? How can we actually add some physical context with this? So this is the project that we're currently working on. It's been sort of a stop and start project. There's been a lot of issues trying to even have access to the data. But the whole idea is that if we can isolate these single pixels in such a way in a data science format, then we can go back and we can create a database of physically real pixels for you to add back in your science workflow. But we can also ask new questions about, are we actually seeing some of the smallest, are we actually observing the smallest observable phenomenon in AIA? So how do we do that? Well, if we add all the spikes back into the image themselves, this is over a single day. If you aggregate all the cosmic ray spikes that hit and 171 over a single day and map them back onto the image, this is kind of what it looks like. You have a lot of cosmic ray hits. Fortunately, the algorithm is pretty good. So if you say, let's say we want cosmic ray spikes that exist in 3 or more wavelengths simultaneously. And I'm using simultaneous in a sort of vague sense because the images on AIA are not taken at the exact same time, but within the 12-second, I guess it would be plus or minus 6 seconds of the time itself. So in a single image run, what is a single pixel, a single cosmic ray occurring at the same time and the same location? So if we say there has to be 3 wavelengths that this occurs in, we can filter out all of the images, all of the AIA spikes over one day and filter it out down to these. But there's still a reasonably high coincidence rate, especially because a lot of these images share a single telescope. So if there's a hot pixel in the CCD that doesn't get cleared properly, you could actually get two hot pixels just sitting on top of each other that are some other systematic. It's not a cosmic ray, nor is it an actual physical event on the sun, but some sort of stuck hot pixel in the image itself. So let's say that we needed something with a 5 wavelength overlap. So that means that these these pixels highlighted in red are single pixel events, these cosmic ray events that existed in 5 different EUV wavelengths over at the exact same time at the exact same space. Okay, neat. We've filtered out these data, so now we have an interesting database. Some of these are associated with coronal hole boundaries, giving rise to the question of maybe there's examples of interchange reconnection happening at coronal hole boundaries. Some of these are associated with active regions, where there are small loops erupting in active regions. But then there are all of these that are off disk entirely. Well, what are those? I don't know yet. But that's something that's ongoing right now. And it's an area where we can use some of these data science techniques to actually do discovery science, to find why are there coincidence pixel spikes that are happening at the same time, the same location in 5 different EUV wavelengths off disk. Is there some other feature that are happening off the disk of AIA that we actually haven't characterized yet, we haven't seen yet? So this is the type of question that I'm saying is well defined once you translate this idea of we have AIA spikes, when are they physical and when are they not, into a data science question. All of a sudden we can query the entire database simultaneously and build up statistics as well as pull out interesting events that are anomalous. So what are we doing well right now? As machine learning and heliophysics come together, what are the things that we're doing well as a community? Well, in general, heliophysics has a large archive of very clean and consistent data. Here's an example of AIA 211 with a noise abatement algorithm that I've applied that you can see that it's incredibly stable. And this is a really unique opportunity because not many other fields out there have this ability to have this large amount of clean data that's available to the public. Certainly in the medical field, they have a large amount of data, but it's all private. In defense, they also have a large amount of data, but that's all under security regulations. But in heliophysics, we actually have a large amount of quality data that is open to the public and encouraged for people to look at. So this provides a really unique opportunity to expand collaborations with computer scientists, with engineers, with statisticians to really explore this data more thoroughly. In addition, some great curated data sets are being developed. And like I was saying earlier, the idea of the quality of data is really key to be able to unlocking the ability to use these algorithms. So Galvez has a paper. This is AIA data that Galvez prepared. It's being hosted at Stanford. It's a small subsampled data set from AIA, but it's incredibly stable, 512 by 512 of the entire mission overall wavelength. So you have a large, stable, well-characterized data set. Georgia State University, their DM lab, also has a really thorough archive of well-characterized statistics taken from AIA as well as other instruments about the features that are involved in there. In addition, software is being developed to be able to use the data and use scientific software in high performance computing environments. So, like I was mentioning, with the efforts to involve Dask, to be able to use SunPy or PyHC or CuPy Dask or Cython, these tools are being developed to actually be able to take the heliophysics data, translate that into a common coordinate system, do any sort of corrections that you might want to, correcting from data number into physical units of emission, for example, to be able to do that in a high performance computing environment. However, we're not doing everything great. There are some room for improvement. So the real opportunities for growth come from being able to merging the data environment and the computing environment. Right now, a lot of the heliophysics archives that exist for both ground and space-based data exist merely in a data service archive, as in the data exists and you ask for it, and then you have to transfer the data someplace else to actually do the computation or ask the science questions that you wish. This is incredibly inefficient, and sometimes it's actually downright impossible to move that much data. So being able to have the computation and the data environments right next to each other, integrated with each other, is essential for moving forward and to being able to use some of these machine learning tools. But it also is a real opportunity for institutions, for groups to come together and cooperate in creating these environments for the researchers to use, to be able to ask for their own questions, to be able to operate on the data in their own way. So another way that we are having a hard time is reshaping science questions into data science questions. Oftentimes what is happening right now is that you have a science question that's being asked by one group or one person, and you have a data science question that's might not have any roots in science that are being asked separately. And those two questions don't really come together and form an actual conversation. So what you get is data scientists finding inane solutions like the sun rotates or there's a solar cycle, and then scientists only being able to look at 10 or 12 or 15 events saying, this is a sample, I'm not sure how common these events are, but here are a few examples of events. And both of those could really benefit from talking to each other. In addition, incorporating the ethical AI standards and principles are really important at this stage. And when I say ethical AI, I'm not talking necessarily about some sort of thing that's very distant from our research, but it's actually something that's very entrenched in the way we do research, which is creating reproducible results, reliable models, reliable results, and something that's transparent, so that if I do something and I make a claim that I have accelerated the WSA model using a neural net, that you can go see what I did and reproduce it and know that it is accurate and it is consistent before you have to take my word for it. So these sorts of ethical standards are incredibly important to include in AI papers and machine learning papers going forward, and especially as you start to involve more machine learning into your own workflows, being able to see what other people do in an earnest and truthful way is absolutely key. We also need to, on that line, we also need to develop consistent and robust label archives with uncertainty. And the reason you need label archives, again, is for that supervised machine learning to be able to be utilized. Without labels, without people taking their time and drawing circles around things that are important, or having clear, concise definitions of what a solar flare is, or what a coronal hole is, or what a sunspot is, it becomes really difficult to be able to actually employ these machine learning algorithms in a consistent and consistently across board and throughout time. And a lot of the modern data sources like SDO are doing this. However, a lot of the legacy data sources could possibly be left behind if you don't have these labels associated with them. So that's an effort that we recently got funding for, which I'm super excited to work on, which is the Macintosh archive, and to bring those labels, those historic labels, up through the current era. We just got started on the project, so I'm hoping that we can take that legacy labels that go back all the way to the 1960s, really got going in the 1970s, and bring them up into the current era. So nearly last, just to sum up everything about helioanalytics, it's really at the intersection of data science and heliophysics, this term of helioanalytics. But ultimately, it's a little bit more than that. It's about bringing in statistics and information design. It's about communicating the process of and how you use data science in heliophysics. It's about presenting statistics on how reliable your methods are and providing error bars. But helioanalytics what we're trying to do is really provide a path forward so that we can blaze the trail for you, and you can actually see how to do these things in a consistent way in heliophysics. More broadly, I think the machine learning in helio community, which has had a few meetings in the past, is a great place to actually come together with like-minded people and share your innovations and what you're doing to bring data science and heliophysics together. So last but not least, I'm going to take some bold statements and present a vision of our near future. So I would say this would be within the next 10 years. I think that machine learning will train models to be able to label data on your workstation at command. So if you wanted to find where all the loops were, all the jets were, all of whatever feature you're interested in, you can pull in the data or have your data environment where you are, and then apply a machine learning algorithm, and it will just go through and label everything in your images. And that would be based on all of the historic labels that have been built up in our community over years. So it will be learned from those labels itself. We'll be able to actually do long-term statistics for solar features. We'll be able to talk about how the sun, how bright points evolve over solar cycle. Are they consistent? Where do they move? How do they evolve? How long does a typical coronal hole last? How long does this typical sunspot last? I mean, these questions that have been able to be answered in piecemeal will be actually able to be answered in statistical ways, and giving you not only what one has done, but what they have all done, what all of these features have done over the lifetime of the data sets over solar cycles. I really do believe that discovery science exists in the realm of unsupervised machine learning, that you can discover high dimensional relationships that have never been observed before, or that would be impossible to be conceived of in our human brains, but that machine learning will give you a window into. So having these high dimensional relationships will be able to understand how the sun operates as a system, and ultimately how the sun Earth operates as a system, and not just in isolated data sets or isolated environments. That being said, people are definitely going to misinterpret artificial intelligence results, especially predictions. Anything that has prediction in it, people will overinterpret it, will misinterpret it, will misunderstand how it's applied, will misapply machine learning and AI techniques. So that's something just to watch out for, because I guarantee you that if it's not happening already, it will be happening very soon, that people will be misapplying these things. However, that shouldn't dissuade us from creating these well-curated databases, because these are incredibly valuable. Databases that have images and labels and metadata will give you a unique advantage if you have access to them. If you don't have access to them, all of a sudden you will be stuck doing incremental science rather than whole system science. So these databases will become key. It's not just about having a database of images, but it's a catalog including labels and metadata. That has been, of course, a trend, or has been around in astrophysics forever. Having catalogs of stars or galaxies have always been there. It's going to become a real issue, and it can become increasingly valuable in heliophysics. Newly graduated heliophysicists will also be data scientists. I think that will really present new opportunities to work across fields in statistics and signal processing and engineering. The new opportunities are emerging, but being able to communicate in this language of data science will really open up doors for you to be able to communicate with colleagues that are across discipline. And finally, data processing pipelines for doing any sort of data prep work will integrate machine learning, and whether that's in situ on board, like on a satellite, or at the telescope itself, that machine learning algorithms will be applied to correct for known occurrences, or in database archives afterwards. That a lot of those prep works, those prep routines that need to be run as a matter of course, will start including machine learning, because these models run so much faster and are so much more efficient. All right. That's everything I have. Thank you for your attention. I hope that you learned something, and I'm happy to answer any questions.
Okay, thank you, Michael. Nice talk. Does anyone have any questions? So there's one question in the chat. Saying that is the algorithm for the data predefined, or does it vary depending on the data?
It depends on the question rather than the data. There are some algorithms that are better attuned to using images, some that are better attuned to using time series, but really the choice of algorithm after you get down to the general class of time series, image, 2D, 3D sorts of parameters, down to what is the question you're looking for? Are you looking for an outlier, or are you looking for the broad distribution of what you're looking, or of the feature that you're looking for? Are you trying to isolate a feature, or are you trying to characterize a set? And so really the science question really determines how you select your algorithm and which one you choose.
Phil?
Michael, I really enjoyed the presentation, very professional indeed. I have a question about the use of these algorithms when you try to, let's imagine you're doing, say, something called data assimilation, as an example. So what you're doing is you're using a set of data and you're updating some boundary conditions according to what you think might be appropriate or whatever. But I want to ask a more general question, and that is, when you mix theory and data together, it's sort of in a fashion like that tends to do. I mean, you have to have some assumptions built into what's coming forward. So, you know, to what extent are you messing with scientific methodology in being able to really refute something? And, you know, it seems to me as if this philosophically could be a little of a skating rink, but maybe there's a clear, maybe this has already been discussed and there's a clear way forward.
So I agree with you that it can be a very slippery slope. But the two keys to remember, especially using a machine learning approach, is that machine learning, supervised machine learning, is only as good as the labels you give it. And so if you are giving, if you're doing a data assimilative approach and you have something that is truly unusual, truly unique, your machine learning algorithm, unless it's been designed to handle sort of outliers, will not know what to do with it. And it will ignore it, or it will misclassify it. And so if you're training on labels, you have to have seen an example of everything, or have a way to characterize true outliers in order to actually apply it. Because otherwise you're going to get wrong results. You know, you're going to misinterpret something. If you're using an unsupervised approach, where you have some sort of model that's, let's say, dividing between, let's use an easy one and say between quiet sun and active regions, something fairly straightforward. You have to be able to have a scientist in the loop to be able to see that and say that that is consistent with the scientific model. Because what unsupervised machine learning will do is it will just draw a line where it sees it a reasonable definition. And so what is reasonable? Well, there's no, that is where, it's very much up for interpretation. So as a scientist, that's where we have to come in and say, what are we actually trying to find here? What are we actually looking for physically? Are we looking for where there are, energized magnetic loops, and that's what we're looking for? Then that's where we draw the line. If it's something different, if we're looking for, emerging magnetic flux from the photosphere, then we need to draw the line there. And so that's really where the scientist has to come into the loop, and that's where the sort of ethics come in, because you can always tweak your data and tweak your lines in order to fit something, but you need to have that sort of forethought and that responsibility to say, this is how I define my question, and this is the result that I get.
So if I can summarize for my own benefit, not only do you have to prepare your genuine data from measurements in a very careful and very clean, documented way that the machine can readily understand, but you also need to really think hard about the question you're asking before you proceed. And then you need to understand, what kind of statistical inferences you're going to try and make, given that you mix up, say, a div B equals 0 with a measurement of a magnetic field. These things can get very tricky, and I find it fascinating that this is going on. I'm just wondering if you think these kind of, maybe that you said ethical, I think they're more methodological questions have really been thought through, or if it's not really relevant and it's just a piecemeal kind of thing. That's my understanding of what I've heard you say. So correct me if I'm wrong.
No, you're right on. And the questions of responsible use, that's sort of the terminology that we've determined, which is responsible use of these algorithms. We're just starting to think about that now. I think there's a group at Goddard that's looking at it, NASA wide, of what does responsible use look like. But coming up with definitions is something that hasn't really been done before, and that's important to do, because until we have community-based definitions of what responsible and irresponsible is, yeah, we are sort of making it up on the fly, and that's not appropriate.
Any other questions? Well, I have one regarding something you brought up in your final slide there, where you talk about the next generation of heliophysicists. Do you see that this is complicated enough that going forward you really it needs to be cross-disciplinary, in the sense of having a heliophysicist talk to a software engineer or someone to do these sorts of problems properly? Or do you think the training for the next generation will be different in such that they kind of learn these things during their training and do it all themselves?
I think the lone scientist, super scientist that can do everything is, I'm sure there will be some people. I don't think it's going to be most people. I say for myself, I couldn't do it. I personally, no. But what it does teach you, if you learn some of these techniques, especially in school, is it teaches you a language to use, to be able to speak a common language, to be able to communicate ideas across the disciplines. So a good example is, label versus feature. So those have boutique definitions in machine learning, in data science world. In heliophysics, if you say I have a label of something, or I have a feature of something, I've identified a feature, or I labeled something, those are sort of synonymous with each other. They kind of can use them interchangeably. And so those kinds of semantics questions are really where I see the benefit, is not necessarily being able to do it all yourself, but at least understanding enough of where the language and where the semantics come in to be able to say, hey, I have an unsupervised machine learning question. This is what my data looks like, to some sort of colleague or another student that has those skills to be able to actually apply the heavy lifting of the computer science side of things.
Okay, we have another couple of questions in the chat, and the first one is there a drawback to the unsupervised machine learning?
Well, sure. I mean, the drawback to the unsupervised machine learning is you don't know what you're looking for unless you know what you're looking for, right? So the unsupervised section, I mean, it requires a lot of heavy lifting to be done by the scientists themselves. I mean, you can't apply an unsupervised machine learning technique and expect to see results that have physically meaningful properties or not. I mean, you can. I think Benoit's on this call. Benoit, he's led this effort to find labels within just an image, and oftentimes it comes back with sort of gibberish. And unless you understand the physical inference of what you're trying to do and are clear with yourself about what that means in the sort of data science world, you could be interpreting something that is not what you think it is and get very, very misled.
Okay, we have a question from Lee Yings. Data volumes are often very different for different solar activity conditions. How does this affect the training of machine learning models?
Yeah, that is a very good question, because data volumes does play a key role in understanding which machine learning algorithms you choose and how you approach the set. There's sort of a minimum that's required in terms of several hundreds of examples of the thing that you're looking for. So if you don't have several hundred examples of whatever it is, and it doesn't really matter what it is, it's going to be very difficult to use a lot of the machine learning tools that are developed. That doesn't mean a data science approach isn't appropriate, because there's a whole new other data science way of looking at things called sparsity, where means that you have missing data, but you understand the gaps in your data as well as the measurements itself. And there's a whole literature based around that. So a lot of if you just go and look up machine learning online and look for techniques, a lot of them will assume that you have hundreds or thousands or millions of examples. And those, of course, are the best to be able to come up with the robust statistics. If you don't have that, if you deal in a very data poor or a data sparse environment, there are other tools, but it's probably not going to be the neural nets and the support vector machines that you come across immediately in looking at machine learning tools.
Okay, we're a little bit over time, but let's go to Gabe for a final question.
Hey, Michael, thank you for the talk. It feels very professional looking. I had a question regarding looking at trying to find a pattern, but in temporal images. So let's say you have a stack of AIA images. Let's say I'm tracking an active region, which I'm not sure how much that has been done throughout the entire lifetime of the mission. But let's say I'm tracking this active region and I'm looking at all the pixels and trying to see how they change, but through time. Do you think what kind of solution do you think would be good for something like for a problem like that?
Yeah, I mean that is a tricky one, because all of a sudden your data volume becomes a lot bigger if you're trying to trace things through time, because you just have more images, more examples. So the solution that we approached when using a UNet approach to label the images before, we used a UNet with a hybrid LSTM. This is a long short-term memory style of neural network. And so what that does is it communicates at a t+1 and a t-1 time step. So it actually has some knowledge of the time evolution built into the machine learning model itself. So using this LSTM UNet hybrid approach, we're able to actually look at some of the contextual images or contextual image. So how the image was a step before and a step after, to be able to help define the image itself. And that really helped constrain the tracking and made the model converge a lot faster. If you're looking at, instead of 2D, if you're looking at 1D time series, there are a lot more tools out there. 2D becomes difficult, but 1D tools are plethora, and there are these things called Muppet models, and they're named because all of the names have Muppet names to them, which is funny. But the Muppet models were developed for language processing, and the amazing thing about these Muppet models is that it creates these contextual chains so that it can understand what this specific word means as it relates to a word in a previous sentence. in science, what we can do then is ask questions of like, did this event that I observed at this time have some contextual relationship to something that we observed at a previous time? And that starts becoming pretty powerful, because then you can start talking about how space weather phenomenon are related to things that happened on the sun, possibly. It's that kind of thing where we have this nonlinear variable time that when we see something happening on the surface of the sun and we observe something happening out in space, there isn't a consistent necessarily acceleration parameter that accelerates the CME or the eruption off the surface. But using these sorts of nonlinear techniques like Muppet models or like LSTM, you can actually start associating events in time, not necessarily consecutive, but with gaps in between, which becomes really key and very interesting too.
Great. Thanks, Michael.
Yeah, you're welcome.
Yes, thank you. And thank you again for the talk, and we will conclude there. Thanks everyone else for coming.
Thanks. I appreciate it. We'll see you later.